Hello, my name is Mihir Limaye, and my colleagues for the internship project are Kaushal Tapray and Pushkar Ubhe. We are in our third year of Electronics and Telecommunication Engineering at Marathwada Mitra Mandal's College of Engineering, Pune, Maharashtra. Let's start with the overview of the internship. C programming tutorial. In C programming tutorial, we'll gain knowledge about the C language right from the basics, that is the syntax, keywords, operators such as arithmetic, bitwise, relational, logical, assignment, and many more, functions and loops. We also wrote many programs and were now ready for embedded C. Now embedded systems programming. We started learning about embedded C and how is it used to program embedded systems. Peripheral programming. We also programmed peripherals like timers, LCD displays, buzzers, matrix keypad, and fans. Project requirements: design, coding, implementation, and testing. For the project, we required MPLabXIDE, PICSimLab simulator, on which we used PICGenios Development Board, and the peripheral devices. We were able to implement and test the project using PICSimLab simulator. Disha workshop. Disha workshop helped us write our resumes, and we got to know about do's and don'ts to follow while preparing our resume. We also got to know about facing interviews and acing them. Now, weekly quizzes based on topics covered throughout the week. With these quizzes, we were able to analyze our understanding of the topics taught and knowledge regarding embedded systems. The goal of the internship. Enhancing our abilities in fundamental embedded programming was the major objective of the internship. Additionally, we were able to strengthen the foundational skills we had in the embedded C programming language and apply them to the PIC microcontroller. This eventually served as the base for development of a microwave oven's user interface. Now, the brief about embedded systems. The definition of the embedded system. An embedded system is a computer system designed to perform a specific task within a larger system. They are purpose-built and tailored to execute a particular set of functions or control specific hardware. Now there are various types of embedded systems. First, standalone embedded system. These embedded systems are self-contained and self-sufficient, capable of performing their intended functions without relying on external resources. Slave embedded system. A slave embedded system operates under the control or direction of a master device or system. For example, a temperature sensor that sends data to a central controller, an input-output device controlled by a microcontroller, a peripheral device like a printer connected to a computer. Then there's oven or a semi-automated washing machine. Next, independent embedded system. It functions as a standalone unit capable of performing its task without direct input or supervision from other devices. For example, a standalone sensor that collects data and stores it locally, a microwave oven with its own timer and cooking functions, and fully automated washing machine. Now, next, real-time embedded system. A real-time embedded system is a type of embedded system which is designed to operate in real time, which means it must respond to external events or inputs within a specified time frame, often with very low latency. For example, airbags in cars, medical devices like pacemakers, consumer electronics like smartphones. Next, networked embedded system. A networked embedded system is an embedded system that is equipped with a network connectivity capabilities, allowing it to communicate and interact with other devices and systems over a network. For example, ATM machines, routers. Now, mobile embedded system. These systems are integrated into devices or platforms that can be easily moved or carried, as they often serve specific functions or applications in mobile environments. For example, cars, robots. Next, hybrid embedded system. These systems are designed to address specific application requirements that demand a combination of real-time control, signal processing, and general-purpose computing capabilities. For example, robots. Project requirements. MPLabXIDE. MPLabXIDE is a development environment for programming microchips microcontrollers, including the PIC16F877A. It provides a user-friendly interface for writing, compiling, debugging, and simulating code for embedded systems. Next, XC8 compiler. XC8 is a C compiler developed by Microchip specifically for their PIC microcontrollers. It translates your C code into machine code that the microcontroller can understand and execute. PICSimLab. PICSimLab is a real-time simulator. It allows you to simulate and test your PIC microcontroller code without needing physical hardware. You can interact with the simulated microcontroller, observe its behavior, and debug your code. PIC16F877A microcontroller. The PIC16F877A is a popular 8-bit microcontroller manufactured by Microchip. It features a variety of input or output timers and other peripherals, making it suitable for a wide range of embedded applications. The development board PICGenios for PIC16F. The PICGenios development board is likely designed for the use of PIC16F series microcontrollers. It provides a platform for testing and prototyping projects, often including features like power supplies, connectors, and LEDs. 16x4 CLCD, that is character LCD. A 16x4 CLCD refers to a character LCD display with a size of 16 characters per line and 4 lines. It is commonly used for displaying text-based information in embedded systems. Tactile switches. Tactile switches are small momentary push-button switches. They are often used for user input in embedded systems such as to trigger specific actions or navigate menus. Matrix keypad. A matrix keypad is an array of buttons arranged in rows or columns. It's used for user input, and the button presses are detected by scanning the rows and columns to determine which button was pressed. Timer 2. Timer 2 are used for various timing and control functions in embedded systems, such as generating delays or measuring time intervals. You can write and compile your code using MPLabXIDE and XC8 compiler, simulate it with using PICSimLab, and test it on the PICGenios development board with various peripherals like 16x4 CLCD, tactile switches, matrix keypad, and timer 2 for precise timing operations. Now I would like to hand over to Pushkar for the design part.
Thank you, Mihir. This is the general design for the project. The microcontroller is the most important component which is responsible for all the computations and operations. It includes inbuilt memory for storing the code and the data generated during the runtime of a program. The PIC16F microcontroller has multiple I/O ports which can be used for interfacing various sensors and other devices. Moving on to the next design of the board we used for the implementation of this project. We have used PICGenios Board available on the PICSimLab software, which allows us to interface the PIC microcontroller with external peripherals such as matrix keypad, CLCD, 7-segment displays, LED, relays, temperature sensors, etc. Along with this, the communication of the pins of microcontroller are also made available on the board externally for ease of access. Now I will hand over to Kaushal to explain the further details about microwave oven and the peripherals used in this project.
Thank you, Pushkar. Now moving on to the microwave oven as a concept. A microwave oven is a compact box-shaped oven that increases food's temperature by exposing it to an electromagnetic field with a high frequency, which enables it to produce thermal energy. Modern microwave ovens use either an analog dial-type timer or a digital control panel for operation. Control panels feature an LED, liquid crystal, or vacuum fluorescent display, numeric buttons for entering the cook time, a power level selection feature, and other possible functions. Microwave control panels are often considered awkward to use and are frequently employed as examples for user interface design. For this project, we will be implementing 4 modes, namely micro mode, grill mode, convection mode, and start, which is a general heating mode. Moving to the microwave mode. In microwave mode, the oven produces microwave radiation, typically at a frequency of 2.45 GHz. Food absorbs these microwaves, causing the water molecules inside to vibrate and produce heat and friction, thus generating thermal energy in a process called as dielectric heating. A few common applications of microwave mode are for reheating leftovers, ready to make microwavable meals, etc. Now, onto the grill mode. In this mode, the food is cooked in the microwave, which emits microwaves, while the grill element, which is a coil which is often found at the top of the oven chamber, radiates heat to crisp and brown the food surface. A few common applications about this are: grill mode is ideal when you want to achieve a browned crispy texture on food surface. Onto the convection mode. In this mode, the convection fan uniformly distributes hot air, enabling baking, roasting, and more exact temperature control, while microwave speedily cooks the food. A common applications about this mode are for baking cakes, cookies, roasting dense meat, etc. And the last mode is a start mode. After you have set the cooking parameters, that is time, power, and mode, and pressing the start button, the cooking cycle is initiated. The oven then operates according to your selected settings. It can be considered as a generic heating mode. The common applications for this are that after setting up the oven for your unique culinary requirements, it starts the cooking process and can be used generally for heating the food. Now moving on to the peripherals. The peripherals used in this project are a matrix keypad, tactile switches, CLCD display panel, and buzzer. A matrix keypad is a commonly used input device in embedded systems and microcontroller based projects. It consists of 12 push button keys arranged in a grid with 4 rows and 3 columns. Most commonly used in telephones, calculators, digital lockers, etc. The 4x3 matrix keypad layout typically consists of numeric keys 0 to 9 and a few additional function keys, which are asterisk and hash. The rows are connected to output ports and columns are connected to input ports. On pressing the key, logic 0 is initiated and a crosslink is established between rows and columns, thus allowing voltage to pass through. When the keys are released, the logic is 1 and a crosslink between rows and columns is absent. Moving on to the tactile switch. A tactile switch, also known as a tactile button or tactile push button, is a type of momentary electromechanical switch commonly used in electronics and embedded systems. Tactile switches are designed to provide tactile feedback to the user when pressed, making them ideal for applications where physical user input is required. Now moving on to CLCD panel. Character LCD displays consist of a liquid crystal display panel that can display characters and symbols in a grid format. CLCD displays typically use a predefined character set that includes alphanumeric characters, symbols, and special characters. The character set is stored in the display's built-in memory. A few applications for CLCD are microwave oven displays, washing machines, calculators, etc. This display is already available on the development board we have used. The next peripheral is a buzzer. A buzzer is an electronic audio signaling device that produces a buzzing or beeping sound when an electrical current is passed through it. Buzzer devices are commonly used for a variety of purposes, including providing audible alerts, notifications, or alarms in different applications. In this project, we have used the buzzer as an auditory indicator to indicate that the timer has ended and the task is finished. Now, I'll hand over to Pushkar, who will explain the overall firmware development process of the project.
Thank you, Kaushal. Moving on to the development process of this project. The overall development process of the project involved the programming of microcontroller using MPLabXIDE software, along with the implementation and real-time simulation of the program using PICSimLab software. MPLabXIDE is a free and open source integrated development environment for developing embedded applications on microchip PIC and DS-PIC microcontrollers. Here, we programmed the PIC microcontroller using Emertxe programming language, wherein we created user-defined functions for setting different parameters such as time, temperature, etc. Along with this, we use some of the user-defined libraries for interfacing the peripherals such as LCD, buzzer, matrix keypad, etc. We wrote individual functions for displaying the power on screen, menu display screen, time display screen, set time and set temperature functions. Along with this, we used a generic delay function to provide delay between the displays. A switch case function was used to select the various modes of the microwave oven, namely micro, grill, convection and start mode. To improve the overall functioning of oven, peripherals like buzzer and fan were used. Now I hand over to Kaushal to explain the further process of implementation of this code.
Thank you, Pushkar. For the implementation and simulation of the code, we have used PICSimLab software. PICSimLab is a development board simulator and real-time emulator with an integrated MPLabX debugger. The MPLabXIDE was used to compile, debug and convert the code to hex format. After that, we ran the simulator after loading the hex file into PICSimLab, which displayed the turn-on screen followed by the menu display. Eventually, we were able to use all of the microwave oven's modes and imitate the functions of each one. Now we will see the real-time implementation video of microwave oven program. So this is the user interface of PICSimLab software, and the board we have used is PICGenios, wherein we have selected PIC16F877A microcontroller. Here we can see the various peripherals explained earlier, such as 16:4 CLCD display, matrix keypad, buzzer and fan. Initially, we need to load the hex file of the program generated using MPLabXIDE into the software. Now we can see the power on screen, and after which the 4 modes to be implemented are seen. The first mode we will be seeing is the micro mode. Here we have set the power to 1200 watts. Now we can see the set time screen where we are setting the time of 1 minute and 45 seconds. On pressing asterisk key, we can clear the entered time, and using hash key we can enter or set the time. After setting the time, we can see the timer along with 3 options like start or resume, pause and stop. We can see the operation of these 3 options on screen. After selecting stop option, control returns to menu display. The next mode is the grill mode, whose functioning is similar to that of the micro mode. As you can see, the repeated selection of start option causes the timer to increase by additional 30 seconds. Now I'll hand over to Pushkar to explain the remaining 2 modes.
Thank you, Kaushal. The next mode is convection mode. In this mode, we need to select an initial preheating temperature of desired value. Currently, we are setting it to 125 degrees Celsius. The microwave oven requires a time period of 180 seconds to reach this temperature. Preheating helps ensure that your food goes from refrigerated cold to blazing hot quickly. Generally, this mode is used for baking cakes, pastries, cookies, and pizza. After preheating, you can set the actual time required for the baking process. Once this time is over, every mode has a feature which uses the buzzer to indicate the end of timer and display the time up message. The last mode is start mode, which is a generic heating mode. In this mode, the timer is set to 30 seconds by default, which can be increased by repetitive press of start option.
With this, we conclude with our implementation of the microwave oven program. Now, the conclusion. The PIC microcontroller on the PICGenios Development Board was successfully used in the embedded system project to illustrate the creation of a sophisticated microwave oven control system. A working microwave oven user interface with improved functionality is the product of the project's lengthy code development, simulation, and testing. I would like to express my sincere gratitude for the incredible internship opportunity me and my colleagues had at Emertxe. It has been an invaluable experience. During our internship, we had the privilege of working with an exceptional team and contributing to meaningful projects. The exposure to real-world challenges and the mentorship we received have significantly enriched my understanding of embedded systems. This internship has been a tremendous learning experience, and I'm very excited to carry the knowledge and skills I've gained into my future career endeavors. Thank you.